Yeah, we're gonna keep it short today because I have an exam to prep for. But this is where we left off last time. So yesterday we learned about the quadratic function, n log n function, and the linear function, and we know the linear function is the best that we can get. And then the n log n is second best. We don't really want n squared, but it can happen. Yeah. Nested loops and the quadratic function. The quadratic function can also arise in the context of nested loops, where the first iteration of a loop uses one operation, the second uses two operations, the third uses three, and so on. That is, the number of operations is n. In other words, this is the total number of operations that will be performed by the nested loop if the number of operations performed inside the loop increases by 1 with each iteration of the outer loop. This quantity has an interesting theory. In 1787, a German school teacher decided to keep his 9 to 10-year-old pupils occupied by adding up the integers from 1 to 100. Yeah. It's for any integer n bigger than 1, we have 1 plus 2 equals to n times n plus 1 over 2, yeah. Cubic. Summation. And I appreciate the new subscribers. Thank you. For example, an integer word containing n bits can represent all the non-negative integers less than 2 to the n. Oh, I see. Okay, yeah, we know this. Oh man, this is such a boring chapter. Yeah, we want constant linear. Okay, so constant or log for data structures, and linear or n log n for algorithms. Okay. Yeah, n log n is barely slower. You can see exponential just go skyrockets. Alright, the ceiling and floor functions. Yeah, I think we know this already. Asymptotic analysis. Thus, we can perform an analysis of an algorithm by estimating the number of primitive operations executed up to a constant factor, rather than getting bogged down in the language or hardware-specific details. Returning the maximum element from a non-empty Python list. Okay, yeah. Big O notation. Let f of n and g of n be functions mapping positive integers to positive real numbers. Oh my brain, bro. Okay. The function is 8n plus 5 is O n. Justification by the big O definition. Oh my. Oh, I see. Okay. So after any starting point n naught, there, if for every integer n after that, if n 8n plus 5 is smaller than or equal to c some constant times n, then that function is on. Oh, so we're basically just trying to bound the function under another function, under another one of the other functions. Okay. Oh, it says it right here. Yeah. Okay, so it is important. All right. This makes sense from calculus, such as L'Hopital's rule, like taking the limit. Yeah, like if you have like a fraction with a greater degree up top and a lower degree in the bottom, then, or if they're equal degrees or the bottom one's greater, then you can take the limit according to that ratio of degrees, and you can ignore like smaller powers. Yeah. Okay, we don't need the proof. We can just say if the fn is a polynomial of degree n, then it is on to the d. Okay, so n squared is bigger than n log n, and okay. Okay. Log n is bigger than a constant. And n is bigger than log n. N is bigger than log n. I thought it's slower. No, n is... log n is faster. What? log n is faster. Oh, this is logarithmic. This is linear. Oh my god, I'm stupid. Okay. Okay, that makes sense. Alright. My bad, I shouldn't be looking at the time like that, but I just have an exam to prep for, so I'm thinking about that a bit. Okay, if it's big omega, then we just take the smaller one. Or the faster one. But who uses these? I guess we can just call it here.